First of all, I would like to thank our Pro Vice Chancellor, Engineering and Technology, Dean, College of Engineering and Technology, HOD, EC Department, all the faculty members of EC Department, and the management for giving us the opportunity to host this event. It's my privilege to welcome you all to this event. Special mention to our invited guest, Dr. Daniele Melati, for gracing us with your presence. Also, I welcome all the participants who have joined us virtually in this workshop. The Department of ECE SRMIST, in association with Optical Society of America and Optical Society of India, is organizing this virtual workshop on photonics and photovoltaic devices, along with the inauguration of Optizen, a student team under SRM OSA student chapter. The Optical Society promotes and delivers scientific and technical information on optics and photonics worldwide that is authoritative, accessible, and archived. The Optical Society's mission is to promote the generation, application, and archiving of knowledge in optics and photonics and to disseminate this knowledge worldwide. I request Dr. Shanti Prince, Professor at Department of ECE, SRM Institute of Science and Technology, the advisor of SRM OSA Student Chapter, and the convener of workshop on photonics and photovoltaic devices to welcome the gathering and give us an overview of the workshop.
Yeah. A very good afternoon to one and all gathered virtually, and a very good morning to Dr. Daniel, our chief guest for the day. On behalf of the SRM Institute of Science and Technology and the Department of Electronics and Communication Engineering, as the convener of this workshop, I hereby welcome the distinguished speaker, delegates, participants, and students who have virtually gathered from different parts of the states and country to grace the occasion on the inauguration of this virtual workshop on photonics and photovoltaic devices, WOPPD 2020. Also on this occasion, we are proud to announce that under SRM OSA student chapter, we are initiating a student team, Optizen, envisioned by a team of enthusiastic students inspired by optics. And the name behind being like Citizen, a team of optical students, we have just coined the word as Optizen because these are inspired by optics. Such enthusiastic students were behind to have this team done. And we are here to inaugurate the same this day. This will be managed for and by students, create valuable opportunities for professional development, and foster lasting relationship between peers and mentors. We are proud to have an eminent person, Dr. Daniele Melati, postdoctoral researcher from University of Paris, France, who is having a passionate commitment to knowledge and research. He is well known for his contribution in the area of photonics. It is indeed our pleasure and privilege to have you amidst us today. On behalf of all who have gathered virtually, I extend a very warm welcome to you, sir. We are really happy to have our head of the department, Dr. T. Ramarao, who has thirst for research and development in our midst today. I have great pleasure in welcoming you, sir, and you've been a motivating factor behind this initiation of this workshop. I welcome our department senior professors and other faculty members who have gathered here virtually to grace the occasion. Our audience really belong to an enthusiastic group. It is indeed a pleasure to have all of you here today. I extend you all a very warm welcome. A brief overview about the workshop. So we run this workshop biennially, and this is the 4th edition. In spite of this pandemic, through the motivation and encouragement of our management, we are releasing the 4th edition of this workshop, WOPPD. The theme of the workshop is, this virtual workshop, basically we aim to provide a clear pathway to understand the research area in photonic technologies available globally to researchers in India. So unlike other editions where we had speakers from in and around our country, this time we have all speakers from international speakers, and hence this paves the way for global understanding of global research, so that more of our big ideas can be transformed into reality. This workshop provides an introductory overview of machine learning for photonics, advantages and limitations of novel design approaches presented by Dr. Daniele Melati. Next day, teleportation on a photonic chip, which will be delivered by Dr. Imad Farooq. Visible light communication and emerging technology for smart city and IoT application, which will be delivered by Dr. Chao Sen. And hands-on session guiding the attendees through the design of their own photonic system using OptiLex, which is an open source optical system simulator guided by Dr. Vivek. The recent trends in optical communications are changing very quickly. It is quite amusing to see that the core of every large communication network carries huge traffic every now and then, which was very much unrealistic 20 years ago. This would not have been possible without photonic technologies. Now there are so many emerging technologies in this list, such as visible light communication, wireless optical communication, all optical computing, AI and ML into photonic systems, software-defined networking, etc. In this workshop, we will be introduced to some of these new frontiers of novel services and technologies. Let this even be a curtain raiser for many activities to follow. Once again, I welcome you all to this virtual workshop and hope that you will have a very exciting and enriching sessions for the next 3 days. Thank you for your virtual gathering. Hope you will be benefited by this. Thank you.
Thank you, ma'am. Essential that the brightest young minds continue to be attracted into careers in this field. SRM OSS student chapter has come out with an student-run team Optizen to kindle the spirit of optics and related technologies among students. I request our HOD, Dr. T. Ramarao, to declare the team open and wish them all the best in their future endeavors.
Yeah, yes, ma'am. Indeed, a great pleasure to say that OptiGen generates a lot of curiosity. It will kindle the doing new things under photonics and fiber optics, optical devices, optical sensors, either on planet or on underwater or over the space. Once again, we're having the pleasure to say, and in the presence of Dr. Shanti Prince and Dr. Daniel and all other invited young light soldiers. Thank you very much for giving the opportunity. Thank you.
Thank you, sir.
Thank you, sir.
Slideshow. Yes.
Good afternoon, everyone. I Pawan Bavaraju, BTech 3rd year ECE, once again welcome you all to the inaugural session of Optizen and WOPPD 2020. On this momentous occasion, I take this opportunity to introduce and brief about Optizen Group. Before I begin, let me start by quoting what Neil Armstrong, the first man to set foot on moon, said. It is a small step for me, but a great leap for mankind. I think these words are relevant here as today we embark on a simple yet challenging and captivating journey of initiating new programs under the Optigen Group. We believe that this initiative will go a long way in development of scientific knowledge and will inculcate the students in carrying out research in field of optics and photonics. The field of optics and its related technologies have been hailed everywhere around the globe as it plays an important part in one's life. Right from our vision to the great speed internet through which we are virtually connected right now. We have also seen how optics has played a crucial role in during these tough times of COVID-19 pandemic. Optigen, which from our point of view is someone who is a citizen of this very important field of optics, is an initiative of the SRM Voices Students Chapter to carry out different activities in the field of optics and its related technologies. Any initiative or any group which is started is not complete without having its own vision and mission. The vision of Optizen is to expose the students to challenges awaiting them in the field of optics and photonics, to create a friendly atmosphere which encourages out of classroom learning experience, and to provide a platform for innovation through practical skills. Missions of the group are organizing workshops, seminars, competitions, and outreach activities to expose students to real-time challenges and encourage them to participate in various events and competitions to enable students face any hurdles in their way of learning and be dynamic along with growing technology. As you are well aware that optics and photonics has a role play to each and every one aspect of research field, our optician group also consists of different domains where students can explore themselves in different areas of interdisciplinary research such as quantum and atomic optics, optoelectronics and sensors, communication, optomechanics, optical materials, and information processing and coding. These domains are further subdivided into various categories such as space optics, visible light communication, role of machine learning and artificial intelligence in optics, to name a few. As a part of this group, we would be working on exciting real-time projects, taking part in national and international competitions in the field of optics, organizing outreach programs so that we give back a part of what we learn to the society. Eligibility to join the club. Students of SRM history of any department from first to fourth year with interest and enthusiasm to work in the field of optics and photonics are welcome to the Optizen group. There is no registration or membership fees to join this group. All you need is passion to work in the field of optics and related technologies. I am immensely thankful to management of SRM, Pro-Vice Chancellor, Dean, College of Engineering and Technology, and HOD of ECE for their support and encouragement in initiating this Optizen group. I am extremely thankful to Dr. Shanti Prince ma'am, who is faculty advisor for this Optizen group, for her dedication and continuous efforts in guiding us all the time in initiating this group. Any group can't start or run easily. The wheels start rolling weeks ago. It requires planning and dedicated work. We have been fortunate enough to be backed by a team of very active and dedicated members who supported us all the time by giving their suggestions and for their enormous cooperation. Finally, I would like to conclude by saying that this Optizen group will be a perfect place to explore and experience the joy of working in the field of optics and enhance your practical skills. With this, I invite the student community to join this Optizen group and assure you that you will have a very rich experience in working in the field of optics, which would be helpful throughout your career path. Students interested in joining this group can register themselves using the link shown on screen. You can contact Dr. Shanti Pinch ma'am or me through the details displayed on the screen. Once again, I welcome you all to this group. Thank you.
Thank you, Pavan. Now I call upon Mrs. Vasanta Dev Suryakala, Professor at Department of ECE, to introduce our speaker, Dr. Daniel Melati, to the participants.
Good afternoon to all. It is my great privilege to welcome and introduce Dr. Daniele Melati, a postdoctoral researcher at University of Paris, to this workshop, WOPPD. So, sir will be giving a lecture on machine learning for photonics, highlighting the advantages and limitations of novel design approaches. So, Dr. Daniele Melati has received the MSc degree in telecommunication engineering in 2010 and PhD degree in information engineering in 2014 from Politecnico di Milano. During his second year of PhD degree, he temporarily joined the Photonic Integration Group at the Eindhoven University of Technology, the Netherlands, as visiting researcher. He started his research activity in the field of photonics, focusing on the definition, development, and exploitation of foundry process design kits for circuit design, including advanced and realistic device models. Within the EU-funded projects EuroPIC and Paradigm, he has been among the pioneers of the novel approach to the design and fabrication of photonic circuits, relying on circuit simulators, PDKs, generic technologies, and multi-project wafer runs. During his PhD, he has largely contributed to the definition and exploitation of reflectometry techniques for the characterization of devices and circuits and has proposed novel device models to predict the distributed effects of the waveguide roughness on guided light propagation. He has also proposed a novel test on wafer approach to map the waveguide optical properties across the wafer area rapidly and accurately. Currently, his main research interests are related to the integration of device models with stochastic techniques for circuit analysis and design optimization, and to the design and development of photonic circuits for mode division multiplexing systems. I welcome you, sir. And now I invite Dr. Daniel to deliver the lecture.
Thank you very much for your kind introduction, and
Thank
thanks
you,
again for having me today. It's really an honor to be with you here for this lecture. And let me share my screen.
Yeah.
Okay,
Yes,
I guess you should see my
yeah,
screen.
it's fine.
Perfect.
Yeah, it's fine.
Yes, sir.
There we go.
Yes.
So thanks again. And it's an honor to be with you today. And as has been said, the lecture today will be about novel design techniques for photonics, mainly machine learning design techniques. And I will try to give you a bit of an overview of the topic and why it's important. And I will focus mainly on the recent work we have been done in the last few years. First at the National Research Council of Canada, where I was before, and then now at the University of Paris-Sud, where I'm now. So first, just a slide to present the group. The group is located in Paris, just south of Paris, and the research center is called the Research Center for Nanosciences and Nanotechnology. It's a joint research center between the University of Paris-Sud and the National Research Council of France. It employs hundreds of researchers and PhD students and postdocs. And the Silicon Photonics group in particular has a wide range of knowledge, of know-how, knowledge, and research topics, basically covering all the aspects of silicon photonics, from silicon germanium structures to strained silicon, modulators, photodetectors, nonlinear photonics, low light. And today I will focus on one of these topics, which is design techniques for photonics based on machine learning, with also some additional subtopics, let's say, related to grating design and subwavelength metamaterials. So this is a brief overview of of my lecture. The main topic, as I said, will be machine learning, but I try to keep this lecture wide enough. So we'll also touch topics related to grating couplers and subwavelength metamaterials. I will try to avoid going too much into details, but obviously, if there is an interest on any one of these topics, I'll be more than happy to answer questions or go into more details if there is an interest. So let's start from some motivation. Why it's important to look for and to research on new design approaches and new design technologies for photonics. So to understand this, we first have to do a little step back and see what we do when we design a photonic design. So the classical design approach for photonics devices is really related to our physical knowledge and intuition. So we decide to design a building block, can be a grating coupler, a multiplexer, a resonator, whatever it is. We start from what we know from physics. We define few variables, few design variables, and we start exploring the design space analytically or semi-analytically, typically through parameter sweep. So we decide the waveguide width, for example, or the length of the structure, or a few other parameters. We use simulators, and we visualize the result of the simulation, like the maps here on the bottom right. And based on this map, we decide what's the best design point, what's the best combination of variables we want for our device. Once we have the building blocks design, we combine them in larger circuit, and we just repeat the same process to design large integrated circuits. This approach has an advantage and a disadvantage. The main advantage is that because we are relying on our physical intuition and on parameter sweep, we gain an analytical approximation of the device behavior, which leads to understanding of its physics and its behavior. So we actually grasp what the device is doing, why it's doing what, and how we can exploit this. It also has a disadvantage though, which is it's very resource intensive. So if you imagine if you have more than 2-3 variables, going all the way through this approach can be very problematic and very time consuming, and we would probably require a lot of computational efforts to do that. So this approach worked very well for decades, but it had started to show its limitation in the last few years, mainly with the growing interest in complex geometries for photonics devices that cannot be easily described with conventional approaches. So you see some of the example here in this slide, starting from photonics crystal, that research topics for that started 20 years ago, and now more recently with the topic of meta surfaces or meta devices, which gained a lot of interest in the last decade. Or again, more complex integrated photonics devices like here in the left of the slide, on the left-hand side of the slide, where you see there are these weird shapes that do not resemble any classical device, but yet are of interest to improve the integration level, to improve the performance of our devices. So when we handle with, once we have to handle with these complex devices, our conventional design approach starts to fail. Mainly for 2 reasons. The first reason is that these devices has a huge number of parameters, ranging from 5, 10 to several thousands, depending on the device we have. And the other problem is that these design problems are often multi-objective. So we don't have to optimize just one particular aspect of the device. We actually have to optimize many of them. So we have a design problem that simultaneously is multi-parameter and multi-objective. So people have started thinking, what's an alternative design approach we can use to handle these problems? And came up with a huge range of possibilities. These 9 schemes actually comes from a publication from Professor Fan at Stanford University, which is here on the bottom. And I invite you to read this paper if you're interested. As you see, most of these design approach depends on what you have to do. So there is no one-stop shop for everything. Depending on the problem you have.
Request the participants to mute your mic.
Sorry. So depending on the problem you have, the best optimization algorithm might be different, and you might have to choose the best approach that works for you. So we can group all of these huge range of algorithms in let's say 3 main categories. One is the global optimizers. These have been used for many years. So for example, the genetic algorithm or the particle swarm algorithms, especially these 2 have been largely used in photonics for years, and they deliver a lot of very nice devices and results. These are global optimizers in the sense that they give us, or they try to give us, the best possible design for our design objective. For example, for the grating can be the most efficient grating for a given geometry. On the other side, so on the right-hand side here in the slide, we have gradient-based optimizers. Those are typically local optimizer. So they won't give us the best possible design, but depending on the starting point we feed the algorithm with, they can give us very good designs. So although these are not guaranteed to be the best possible ones, the advantage is that these algorithms are much faster and can be very efficient. In the middle, if you want, we have all the modern approaches, which is related to machine learning and artificial neural networks that can play several roles, being started from let's say surrogate modeling to global optimizer, depending on how we use these schemes. So a lot of devices has been designed now using these different algorithms and approaches. You see here just a slide with probably the two most famous that have been proposed in the last year. On the left-hand side, you have a meta-grating, again from Professor Fan at Stanford, that was designed using an artificial neural network. And on the right-hand side, you see an integrated WDM splitter. This device is only 2 micron by 2 micron wide, and was proposed a few years ago by Professor WOPPD. And you see on the bottom right that it's capable of splitting the two main communication bands, so the 1300 and 1550 nanometers, with an extremely compact device. You see both of these devices are not described by a classical simple geometry. It's more like a Gruyère cheese, if you want, on the right-hand side, where it's a pixelate device, where it's not obvious why the device works. The only thing we know is that the device works as it's expected. Both of these devices have thousands of design parameters and will not be possible, absolutely not possible, to be handled with classical approaches. And that's the reason why they were designed using these novel techniques. So we have a lot of advantages using these novel design techniques. We also have drawbacks. So for example, local optimizers, as I said, they're extremely critical on the initial guess we provide. So they can give us a lot of good results, but this is conditional to the fact that we give them a good starting point for the optimization. If we just throw them a random starting point, almost surely we will not get anything good out of them. As for the other ones, we are still stuck with several problems. One typical one is multi-objective optimization, as I said. So if we don't have one goal in our optimization, let's say the grating coupler, we're not just interested in its coupling efficiency, we are also interested in the bandwidth, in the size of the grating coupler, then this problem becomes much more complicated to solve. And it takes a lot of effort and craft to design the proper objective function, the proper goal of our design. And a general problem that's true for all of these approaches is that they are sort of a black box. So we throw them a geometry we want, we throw them a design objective, and they work for hours or days. And after that, we have a solution. We don't know anything about this solution. We just know that it works. We don't know why. We're just happy with what we have, but we don't really gain any understanding of the physics of the device or why a specific device works that way, or it doesn't work another way. So today I will try to present you an approach that combines two different techniques, which is gradient-based optimizers and machine learning, to try to address a little bit this limitation and come up with yet another design approach that try to solve this. So first of all, really 3 slides on machine learning and artificial intelligence. I am a photonics engineer, not a computer scientist. So I am a user of these tools, not a developer. So what is machine learning? First of all, machine learning is all the science that studies the construction of systems that can learn from data. So this clearly includes a huge number of possible algorithms and techniques. And in the last few years, the particular class of algorithms that gained a lot of interest were artificial neural networks. Today, you'll see later in the talk I will not present anything related to artificial neural net, but I will present you a different kind of machine learning, which is somehow simpler, but has been known for probably more than a century. So when we talk about machine learning, we normally talk about two different things. The first one is supervised learning. Supervised learning works this way. So we have a bunch of data which are in the form x, y. So we have an input, x, which can be a vector, and we have an output, y, of a function that we don't know. We only know the input and output of this function, and our goal is to find an approximation for this function. So the goal is to find a function f such that f of x is roughly equal to y. This is called supervised learning, and it can be used for a wide range of applications. The first one which can come up to mind is regression, for example, but it can also be used for other techniques like classification, or deciding, for example, if images are images of cats or dogs or not cats. We have another form of machine learning, which is called unsupervised learning. In this case, we don't have a function output. We only have a set of vectors x with no other knowledge of the output. So it's not even important we have a function here. We just have a group of data. And we want to find a structure in this data. So for example, on the bottom left side, you see we have a bunch of pictures of fruits, which are apple, oranges, or pears. And we feed all of these data to a model, and we ask the model, can you see a pattern there? Can you divide different type of fruits? Another form of unsupervised learning is the so-called dimensionality reduction. So we have, again, a group of data that are described by a large number of variables, for example, are 3D vectors or 5D vectors or 10D vectors. And the question we ask our model is, are all of these variables really necessary? Or can we shrink down our our space to a smaller number of variables, but retaining all the information that's in the data set? This type of machine learning is exactly what I will exploit today, and is the base of the technique I will present you today. I will do this through an example, which is a very interesting example because it's based on a photonics device that has been used widely through many applications of photonics, which is a grating coupler. So a grating coupler is typically used to couple light from a photonic wire to an optical fiber. And it just consists of a periodic arrangement of waveguide discontinuities. And you see on the bottom right here, the slide. So the light impinges on these discontinuities, and it's scattered all over the place. So it's uniformly scattered. But if the scatterers are designed at a proper distance, then for a certain angle out of plane, all of these scattered fields will be in phase, and so they will propagate at that particular angle. This has been known for years and has been used, as I said, in many technologies and many variations and forms. So the angle is decided, as I said, by the distance between these scatterers. The efficiency of this device depends on many things. The first one is the directionality. So these scatterers here are uniform scatterers. So they are symmetric, so they scatter light everywhere. In particular, they scatter light upward and downward, but our fiber typically is placed on the top side of the device. So we want to have a large fraction of this power be scattered up, not down. This is the directionality. Then there is the mode overlap with the fiber mode. So this particular device will scatter a field with a certain shape that's not necessarily the shape of the fiber mode. So we have to design our grating to match as much as possible the fiber mode. And then we have part of the light that's actually not scattered out, but is scattered back. And that's for what's concerned here, that part of the light is lost. So all of this is known, but there is a particular condition that's very interesting and very difficult to achieve, and that's vertical emission. So as I said, changing the period of the grating, we can change the angle. And there is one particular angle, which is 0 degrees. So perfectly vertical, if you wish, exactly vertical out of plane here, which would be very interesting because it would make a lot of application and system much easier to handle. For example, fiber arrays or VCSELs, even free space design systems. If you scatter exactly vertically out of the chip, all the alignment and the system design will be much easier. But this has a main issue. It's possible to design a grating with a 0 diffraction angle, but if you do so and you look at the grating equation, you discover that at the same condition for the same exact period, you also satisfy Bragg condition. This means that a lot of power will be back reflected. More than 30% of the light will be back reflected. So you can design a vertical grating coupler, but this normally comes with huge back reflection, which is a loss for what concerns fiber couplers, but it also can create a lot of problems for other devices that are in the circuit before the grating, because huge reflection normally disturbs the proper operation of photonics devices. So with this scenario in mind, we want to set up a very difficult problem here, because that's what makes this design interesting. We want to design a grating coupler that has a perfectly vertical emission, but simultaneously also small back reflections, which we have already seen as a tough problem. On top of that, we also wanted the grating to be highly efficient and to be wideband. So we want to cover a large fraction of the communication band, so we can use this for WDM application, for example. So this is a very interesting problem because it's difficult. So how we can do this? What's our strategy here? So the first thing we can imagine is we want to do this. We want to have a grating that is small, that is very short. So we only want to use 5 periods in this case. Just for a comparison, normally grating couplers have 15 to 25 periods, so are several tens of microns long. In this case, we want the grating coupler that's extremely short, just 5 periods. The reason is that this will guarantee us a very wideband operation. And the reason is that with few periods, we have to keep the proper phase relation on a short distance, and this will guarantee wideband operation of the device. Obviously, this as an immediate drawback. Short grating will give us a wideband operation, but will give us a very small efficiency because we will only have 5 scatterer to scatter light out, all the light out of our waveguide. So how we can counteract this? The solution is to use this weird geometry. Here you see a cross section of the device, and you see that in one cell, one period, we have this sort of L-shaped scatterer, and in front of it another silicon sort of pillar. This geometry has already been demonstrated to be extremely efficient because it guarantees that most of the light is scattered upward, and it also allows to control how much light is reflected backward. This has already been demonstrated. So we choose this solution because we know it's very efficient and can allow us to scatter a lot of light in a small number of periods. We also do another couple of tricks to improve the efficiency of our device. The first one is to use a silicon core that is 300 nanometer thick. As you probably know, the standard silicon core is 220 nanometer thick. But if we increase the thickness, this will also increase the scattering strength of our grating coupler. So it will allow us to have a shorter grating with a higher efficiency. The last trick we do is that instead of having an exactly periodic structure, so with 5 periods all equal to each other, we allow the first period of the grating here, you see here in the figure, to be different from the other 4 periods. This technique is called apodization and allows us to shape the scattered field of the grating to better match the mode of the fiber that's on top of it. So we have a lot of tricks in this design, and that's nice because we have just set up a problem that is multi-objective, as I said at the beginning, because we want high efficiency, small back reflection, and large bandwidth. So we have 3 goals here. And we also have 10 design variables, because you see each cell, each unit cell of this grating has 5 lengths. So the distance of the pillar from the previous cell, the width of the pillar, the second silica gap here, and then the 2 lengths of this L shape. So it's 5 variables for each period. And so in total, we have 10 variables, 1 for the first period, sorry, 5 for the first period, and 5 for the remaining 4 periodic section. So it's a multi-objective, multi-variable design problem that we want to solve. And how we're going to do that? We use a technique that we name global mapping, which is based on local optimization and pattern recognition. And it's a technique that cascades these 2 approaches and allows us to design problems with a fairly wide number of design variables. And I will go quickly through all these steps. So we start off with a local optimizer. So as I said, these type of optimizers are extremely sensitive to the starting point. And they work normally based on gradient. You see here on the bottom right a representation of how these algorithms work. You start from an initial guess, which can be the crosses here in the blue or light blue areas, which is a combination of design parameters. And then you ask the algorithm to find an optimum of your objective function. This is sort of what would you do if you have to climb up of a mountain and you don't have a map. The only thing you can do is to measure the gradient of the mountain and just proceed toward the direction of the maximum gradients. That will guarantee that at a certain point, you will reach the top of the mountain. But as I said, it has a drawback because depending on where you start from, you might end up on another hill, on a different mountain. And you don't know because you don't have a map. So what you can find, the best you can do with these algorithms is to find a local optimum. So something that satisfies optimality only locally, but it won't guarantee you a global optimum. So what we do here, how we can exploit this? Well, we select what we say a primary design objective. So out of the 3, we say the most important one is fiber coupling efficiency. And then we launch our local optimizer many times. You see here on the top of the slide, on the blue dots, a lot of different starting points. And we ask the optimizer to run optimization. Some of these optimization will end up in nothing, just garbage designs. But some of them, we actually get very interesting designs. We operate and we start collecting data, which are the red dots here. Once we have enough data, in this case, few less than 10, let's say, we move to the second phase. The second phase is the properly machine learning phase. And we ask this question. With our grating, we have 10 different variables, as we saw. Are all of them really necessary or not? So on these bunch of red dots, which are our data, we apply a dimensionality reduction. In particular, we apply principal component analysis. As I said, principal component analysis is one of the machine learning dimensionality reduction algorithms have been known forever. And the goal of this analysis is to reduce the number of correlated variables, in this case 10, into a minimum set of uncorrelated variables, but retaining most of the original information. This is a nice picture in 2D of how this algorithm quickly works. Imagine you have a bunch of data, which are the X here on this graph, and these are described by 2 variables, which are X1 and X2. But you also notice that are mostly aligned along this red line here. So what you can say is that, well, I redefine my variable space, and I will use only one variable, so that's Z1, which is actually is aligned with the red line here. And I will project all of my data, the axis, on this red line. On doing this, I clearly do a mistake. I have an approximation error, but I gain something in between. I will move from an R2 description to an R1 description of my data set. So instead of two variables, I will only use one variable. And I will just accept a small approximation error. So if you want it in a formula, it's like here on the bottom right. So you have a vector of which is m-dimensional. In our case, would be a vector which is 10-dimensional, and you describe it as a sum of vectors with proper coefficients. And if you use a small number of coefficients, then you just use the coefficient instead of the vector to represent a particular point, which is exactly the same that's represented here in the graph. So we do this, and we feed our red dots to a principal component analysis algorithm. And what turns out is that out of the 10 variables, well, only 3 were necessary. So we scaled down the problem from a 10D problem to a 3D problem, doing this and retaining essentially all the information we had. Why this is important, or why this is advantageous? Well, it's because now it's a 3D problem. So what we can do is to just proceed with what's just a very standard and very classical design approach, because we don't have 10 variables now, we only have 3. So we can do parameters sweep, for example, and explore the design space. Even if it's multi-parameter, we can explore it exhaustively, thousands of times faster than we would do in 10D. Keep in mind that exploring a 10D design space, just doing parameter sweeps, so sweeping all the possible combination of 10 different variables, might take billions of simulations. So it might take, I don't know, tens of years to explore a design space like that. In this case, it's only 3 variables, so it's much, much, much faster. We can identify global optimum. We can do multi-objective optimization, and we can also gain some physics insight. That's all I'll show you in the next part of the talk. So we have a nice design approach that allows us to explore how a device works. So this is a result for our grating. Remember, we started from 10 design variables and we shrink it down to 3. So we have 3D spaces, and the 3D spaces are plotted here for our 3 different design objectives. So coupling efficiency, back reflection, and bandwidth, in particular 1 dB bandwidth of the design. So you see immediately we have a picture of possible interesting design area within the design space. So far, we didn't really do a design of the device. We simply explore the design space. We have just, it's the same we do with classical design. We have just done parameter sweep, and we have maps of design objective or parameters for the device, and we're just visualizing the results. So now we can enter the real design phase of our device. And here depends on what we want to do. So for example, the most simple design we can imagine is that I'm only interested in coupling efficiency. That's our bottom line. It's just a single objective. I want just to maximize coupling efficiency. Well, that's easy. You just go into your 3D map and you pick up the highest coupling efficiency in the first map here. And here on the bottom of the slide, you see a cut through the gray plane here. And in this case would be design B, you have your maximum efficiency. But you can also come up with something more complicated that takes into account many design objectives, as we said at the beginning. So for example, we want high coupling efficiency, sure, but we also want reflections to be smaller than minus 20 dB. This is normally what it takes to have a usable device. And we also wanted the coupling efficiency to be extremely high, above 150 nanometers. This bandwidth is really huge for an integrated photonics device. So if you put these three objectives in place now, well, you do again a lookup on your maps and you come up with design A. You see that compared to design B, the coupling efficiency is slightly lower, but in return you have much smaller reflections, and you see here that design A is in the blue area, not in the green area here. And also the bandwidth goes up considerably, moving from design B to design A. To better appreciate this is a plot versus wavelength for coupling efficiency and reflection. The blue line is for design A, so our multi-objective design, and design B if the orange line for design B, so where we only are maximizing coupling efficiency. You see, design A loses a little bit on maximum maximum efficiency here. We lose about 0.2 dB, so it's a tiny cost we have to pay. In return, we gain 30 nanometer more of bandwidth. So you can compare the orange line with the blue line here. And these, the 1 dB bandwidth of the design A is almost 160 nanometers. And it covers basically almost the entire span, covering S, C, and L communication bands, which is huge, with only 1.3 dB penalty in the coupling efficiency. This is very remarkable. And if you look on the reflection, it's probably even easier to appreciate how different these designs are. Keep in mind that these are two different designs of the same device. So the basic structure is exactly the same. We are just using a different combination of parameters. You see, design B has a very small reflection at 1550, so it's almost minus 25 dB. But it very quickly goes up if you get out of this optimal point. While if you look in comparison, design A, sorry, its reflection is below minus 20 dB for, well, basically more than 200 nanometers. So even if at the 1550, its reflection is slightly higher. So you see how the device behaves completely different, even if the basic geometry is the same. Now, what's the best design? There is no answer to that because it's a heel-pose problem. There is no best design. That depends on your application. If you really need to nail down the reflection and the coupling efficiency, and you're only interested in working in a 1550, then probably design B is good for you. But if you're interested with a device that works on a WDM signals at a very low back reflection, wide bandwidth, then design B is not good for you. Then design A works better for you. So the best design really can be chosen at the end of the design cycle, not at the beginning. And if your design goals changes at a certain point, the only thing you have to do is just you pick up another design from your maps. You can also go fancy and do other exploration on using your maps. For example, you can do what's called a Pareto frontier optimization. So you can ask yourself, what is the maximum coupling efficiency I can get for a given operational bandwidth? And you see this is a line that responds to that. So the wider the bandwidth you want, the smaller the maximum coupling efficiency you will get from this design. And there is no way out from here. So if the bandwidth you need is around 170 nanometer, you will never get a device that works above 80% efficiency. And this gives you a lot of information on what you can do and what you cannot do with this device. And if you see this in perspective, this kind of information will not be possible to get from a classical optimization approach, because the only thing you would get is a single design, and you will never know where this design sits in this curve. You really need to explore how the design works, or the device works, to be able to draw this kind of analysis and lines. You can also, I don't have time now to go too much into details here, but you can also have some physical insights analyzing the maps we have seen before. For example, you can understand what is contributing to the efficiency of the device in the structure. if you do this kind of analysis, which requires a correlation analysis and some investigation on the reducer design space, you will discover that you see on the bottom here the unit cell of our grating. You will discover that the coupling efficiency of this grating is determined by the entirety of the structure. So each single section in the unit cell contributes to the scattering strength and to the coupling efficiency of the grating. You also discover that the back reflection is not due to the entire structure, but it's mostly controlled only by the first three sections, essentially by the pillar, the silicon pillar we have in front of it, and the distance of the pillar between the other sections. So this is, again, it's a kind of analysis and physics insight you will not get using a classical design optimization approach. Another type of things you can do is to combine these with, again, another machine learning algorithms, in this case, a supervised learning, to do some statistical analysis. The results shown here are based on polynomial Gauss expansion, which is a sort of a type of surrogate modeling. And this is an extremely efficient way to understand the question. I get a very good design. It's very high efficiency and very low back reflection. But what happens when I fabricate it? Is it really going to be robust or not against fabrication errors? This is a way to do a statistical analysis and analyze how your device responds to the unavoidable uncertainty of fabrication. So in the last part, the last few slides, I will introduce another nice trick we can get in our grating design, which is the use of subwavelength metamaterials. You might have noticed in one of the previous slides, let me go back a little bit for a second, here, these devices work greatly, but they have a small disadvantage. And if you look carefully here, this is the length of its sections in the device, and these lengths are expressed in nanometers. You see that these particular designs have a minimum feature size in the order of 40 nanometers. So if you have experience with fabrications, 40 nanometers is really at the limit of what nanofabrication can do today. So a question we might have is, can we have a grating which has a very high efficiency, so same great properties we have seen so far, but also has a larger feature size, let's say in the order of 100 nanometers. So 100 nanometers is something we can do with deep UV lithography, which is the fabrication techniques that's used for mass production. So the answer, yes, we can do that, but we have to introduce an additional tricks to all the other tricks we have used so far, and it's the use of metamaterials. So just in 3 words, what's a metamaterial? Well, it's essentially, it's a grating again, but where the pitch or the period of the grating is much smaller than the wavelength of the light that crosses the structure. If we do this, we ended up working on this area of the Venn diagram, so in the so-called subwavelength regime, where we suppress all diffracting effects, and we can approximate how our grating has an homogeneous material with a different effective refractive index. So what we can do actually using metamaterials is to design an artificial material which has a refractive index in between silica and silicon. This is very interesting because it gives you a lot of design flexibility for your photonics devices. So a lot of information are in this Nature review published a couple of years ago, which I really encourage you to explore to get a lot of information about subwavelength grating metamaterials. So for what's interesting here now today is how we can explore these metamaterials inside our grating design. So we can work on the transverse direction and slightly change our geometry. So on the top right here, you see the geometry we have used so far. And we have discovered that the small feature is actually due to this silicon pillar we have in the structure. So what we can do is just, we get rid of that silicon pillar, and instead of it, we use a subwavement metamaterial. So we replace it with a grating, which is in the transverse direction now, not in the propagation direction. And we can approximate this new grating, like you see here on the bottom of the slide, this additional grating, we can approximate it as an artificial material with a different refractive index. So now the structure is slightly different. We have 4 different sections, so 4 different lengths, but we also gain the possibility to design the refractive index of this additional section here, which is a possibility we don't normally have when we use silicon photonics, because we cannot change the refractive index of silicon. While now, because we're using metamaterials, we also gain the possibility to change the refractive index, at least in one of the sections. So we do exactly the same process we have done before, same design approach, same idea. In this case, we end up with a design space that only has a reduced design space, sorry, that only has 2 significant variables. So instead of 3D maps, we have 2D maps, and we do the same process again. In these maps, we analyze what is the minimum feature size, and very interestingly, we find a lot of devices which has a feature size above 100 nanometers, and even more interestingly, we find a region which has a feature size above 130 nanometers. These kind of feature size are very robust on fabrication and can be easily mass produced in any silicon photonics foundries nowadays. You see, this is another, it's again a wavelength analysis of their performance for both back reflection and coupling efficiency. You see they remain very high efficient, even if the feature size is much wider. So this is very nice, because with this same design approach, we design in a design space that it's so-called not homogeneous, because we have length to design, we have refractive index to design, and yet we are able to find very good and performing designs. Just very last slide, really, just to prompt you and show you that these and demonstrate you that this design approach is capable to handle problems that are not just related to grating couplers, but can handle any type of design problem in photonics. These are just the results that that comes out from the design of a power splitter. So this is a completely different problem, completely different topic. We are designing a 50-50 power splitter 1x2. We start from a geometry you might recognize, which is a multimode interference coupler, which is classical and well known. And we threw this to our design scheme, and we ask it to optimize decoupling efficiency. And you see here again 2 of the design results, and you can probably appreciate here even better how different these designs are. The shapes of the output design is completely different, and yet the coupling efficiency is sort of similar. There is roughly 1% difference in the coupling efficiency, but their spectral behavior is totally different, both for the coupling efficiency and the back reflection of these designs. You see design 2 pays about 1% in efficiency, but it gains 10 dB in reflections, and its operation is way more wideband compared to design 1. So again, completely different solutions for the same design problem, for the same base geometry. Again, what's the best design? That's a question that depends on the application you have. So this brings me to the conclusion. I hope I've been able to highlight here today how photonics is really becoming a complex field that involves a lot of different techniques that are not just related to physics, but involves also data science and involves also optimization algorithms. And the reason is that novel devices, novel materials, and the possibility to include metamaterials, for example, are transforming photonics design into a multi-parameter, multi-objective design problems that cannot be easily handled with classical approaches. So someone said that machine learning might replace human intelligence at a certain point. I sort of strongly disagree with this. I really believe that, on the other hand, machine learning can be a tool for us for understand more complex problems, to give us a broader view of photonics devices in this case, and to extract information, to visualize the outcome of our design, to get intuitive understanding, to get physics insights, and above all, to inspire us with new design ideas, new photonics design devices that will be at the base of future application, and will end up expanding a so-called photonics design library that's available for not just for communication problems, but all range of new applications that photonics is gaining day by day. So thanks a lot for your attention, and I hope you appreciate the lecture. If there is any question, I'm more than happy to answer.
Thank you, sir.
Thank you.
It was a very great learning for us. It was very informative to hear about topics like designing techniques, and also the role of AI ML, the greater couplings, the metamaterials. It was very informative for all of us. I request the participants to post their questions in the chat box if they have any. And also, sir, I personally had a doubt. It was very interesting for me. So, sir, what parameters should we consider while designing to get the maximum efficiency?
For the grating, you mean?
Yes, sir. Yes, sir.
So the question is actually very difficult. Let me go back a few slides. So as I shown here, this is probably the best slide. As I shown here, the efficiency of the grating, which is defined on how much power we are able to couple from the photonics wire all the way to the fiber, depends essentially on three things. Depends on how much power we are able to scatter up instead of down, how well we are able to suppress back reflection, so to suppress the amount of power that goes back, and how well the scattered field of the grating matches the field of the fiber, so the mode of the fiber. So we have to simultaneously play with all of these three aspects to gain the maximum efficiency. And how we do this, well, that's depend on the geometry. In this case, the geometry is made of 5 different sections. So we have a pillar, we have the distance of the pillar between with the silica gap, and we have the L shape. So we have to design simultaneously all of the 5 lengths here to maximize the efficiency. And that this has to be done simultaneously. We cannot do that one by one. And that's the reason why this problem is particularly difficult. In a classical, easy, let's say basic geometry, you will only have one pillar. So for example, I have a picture here, like this one. So the only thing you can do here is to design the period and design the duty cycle. So how wide are these pillars? But you don't have any other design parameters here, only these two.
Yes. Okay, sir.
I just have a question.
Sure.
Upon applying principal component analysis for dimensional reduction, you have reduced the parameters L1 to L2, finally 3 parameters.
Yes.
Will you be able to link back to which 3 parameters among L1 to L2?
You won't be able to track them back in the sense that the 3 parameters, the 3 reduced parameters, are not directly related to a physical dimension. They're a blend of all of the 10 simultaneously. Yes. What you can do,
more correlated. Yeah.
They're actually uncorrelated. between themselves, but they're correlated with the original 10.
Data. Mm.
So what you can do is to ask a different question: is these three parameters, how they contribute to the different performance of the grating, which was what I tried to explain with very quickly with the slides on physics inside. So, for example, one of the parameter of the reduced parameters describe a certain combination of the first three L1, L2, L3. And that is the parameters that control back reflections. So it's not directly physical parameters, but you can understand that that's the parameters that tune the back reflection of the grating.
So intuitively, you have to link back to these parameters for fine-tuning the design.
Yeah, you can do that. You can say, now I focus only on these because I want to fine-tune a little bit just the reflection, and so I would just touch that single parameter.
Okay. So at any point of time after dimensional reductionality, you will not have the correlation between the taken parameter and the reduced components.
Well, you will have the link. Now, what with uncorrelated, I mean that the reduced parameters themselves are guaranteed to be orthogonal by the algorithm.
Yes,
so the three of them are completely orthogonal, so they're uncorrelated. But they're obviously correlated with the original one. So you have a relation, in this case it's a linear relation. Let's see if I can quickly find it. That links, which is this one, that links the original and reduced parameters. So you can go back and forth the two spaces anytime.
Okay. So a little a priori knowledge will be required to fine tune.
Yeah, I don't know if a priori or posteriori, but yes, you will need some knowledge on the device, and that's in a sense is a little bit the strength of this approach, because it's not black box. It gives you a tool to understand what you first need to understand how the device works a little bit, and then it gives you another tool to understand the physics behind it.
Okay. The entire work is simulated, or you do take to the fab lab and do it and then verify the coupling efficiency?
These devices actually have been fabricated a month ago, so they're in lab now.
Okay.
So let's see how they behave in reality. Let's say on the on a real device. But yeah, so far these are simulation results.
Okay. And which tool you just used to carry out these simulations? You build your code? No, you build your code for these simulation work, or a ready-made package tool which you use for this work?
The code for principal component analysis on all the framework is was developed by us. It's actually freely available on GitHub if people want to explore. You can just send me an email. I'll give you the link to the code. Okay. For the simulation part is actually relies on a numerical FDTD solver. So we didn't write our FDTD.
So after doing this PC analysis, then you feed in the data to the numerical, and then you try out the simulation.
Yes, exactly.
Thank you. It was interesting. So maybe.
Thank you.
It was basically the photonic device design was trial and error based. Like now it has got a shape and a model now how to actually go through with. Like earlier when people started working, just reduce this, increase this, and it was basically a trial and error method approach was there. Now, after these ML came into picture, there's some reasoning behind why we have to go for this. Yeah, that was interesting. Thank you.
Thank you.
Any participants who want to post your question to sir, you can unmute yourself and you can ask.
One of the participants have asked that can we use this code in V software?
Not sure what's V software, but the code is written to be general enough. So the code that's available, I was mentioning, is available on GitHub, has already a module to interface it automatically with numerical FDTD, but the code itself is generic. So it's possible to write a new plugin module and interface the code with anything else. It doesn't have to be, it doesn't even have to be Photonics device in principle. It can be anything.
Okay, sir.
Any other participants who want to interact with the speaker? You're most welcome. You can raise your hand or you can unmute yourself and pose a question to sir.
I can also do this if you want. I can. There is my email on the first slide here.
Maybe they can contact.
So if anytime you have any question or any other comment you want to give me, just drop me an email. I'll be more than happy to answer.
Yeah, Dr. Daniel.
Yes.
Yeah, so that was very interesting talk. I think you just gave us a crisp presentation on how we can incorporate this machine learning techniques in photonics. So what basically I understood was we are just trying to improve the performance of these photonic devices by having some additional machine learning techniques. Am I right?
Yes. It was, let's say, improve the performance in general, which means a lot of things, which means make it more efficient, more compact, more wideband. So yes, all of these together.
Okay. Because what I felt from that grating concept was the separation between the two gratings. That is one of the important parameters in the design. So from the theoretical analysis, I think we should be able to gauge what can be the approximate separation. So what exactly can we do from this ML?
Well, from a theoretical and, let's say, analytical analysis, you can get an idea of how the device should work. For example, you can get an idea of what's the period of the grating could be. But you won't be able to just analytically describing the grating in a way that's sufficiently detailed to give you the value of the 10 parameters.
Okay.
That the geometry in this case is too complex to be analytically approximated with the sufficient detail. So that's why some optimization tool is required. So the grating, once you leave the, let's say, the basic geometry of the grating, that's a single edge or even double edge structures, beyond these 1-2 parameters, you won't be able to do it manually. You have to rely on some sort of optimization approach. And if you explore a little bit the literature on, let's say, of the few last years on grating couplers, you see that most of the complex geometries that have been proposed and demonstrated for highly efficient designs are all based on some sort of optimization. Normally, it's a genetic optimizer or particle swarms. And the reason is that if you want to go very high with performance, you have to go very complex with geometry. And these increase the number of variables. So you're essentially stuck. You don't have an analytical model for that.
Okay. But as we see that even though after fabrication, there are some tolerance in the performance of the design.
Yeah.
Say if we have this SOI photonic device, if we say take a ring resonator. So if we design it for a resonant wavelength of 1550 nanometers, but I don't think we can try maximum possible analysis and we can have it resonant at not exactly 1550, but at least 1549.5 or something, a slight gap of a few nanometers. So can we have some additional ML techniques which can give us some additional information about what exactly can be the fabrication tolerance?
Yeah. So yes, that was one of the, it was in one of the slides, I guess. Let's see if I can find it. Yes, in this case, if your fabrication tolerance is the parameter you are mostly interested in, then that can be one of the design parameters. And for example, you might choose a design that on paper is not optimal, but in the sense that it's not the most efficient, but it gives you the highest resilience against fabrication errors. For example, this was done doing a statistical analysis. So if you know how the performance, how the fabrication introduces errors, what kind of errors the fabrication introduces, you can inject these in your simulations and do a statistical analysis using a machine learning approach in this case to make it efficient. And in this case, you see in the graphs here, these are probability density functions for the coupling efficiency and back reflections. And you can set a threshold, for example, and say, I want the most, I want the design that guarantees the highest chances of being on spec. And you see different designs as completely different probability density functions and completely different fabrication yields.
Yeah.
Which one is the best one? Well, it depends again on your goal. So if you want the design to be very robust against fabrication errors, then you will pick the one with the highest yield in this case, even if that is not the best one on paper. Almost surely won't be the best one on paper in terms of efficiency.
So can we expect better fabrication tolerance by using such ML techniques?
If you include this type of information in the design flow, yes, absolutely, yes.
Okay.
Sure. But you need to know how the fabrication is going to impact the design.
Yeah. So if we say take an example of this micro ring resonator, so the gap spacing between the ring and the bus waveguide is one of the important parameter, which is going to decide on the coupling efficiency and other things.
Yeah.
And also, I think the width of the waveguide is also an important parameter.
Yeah. So you need to know how your fabrication, how the process you're using, what are the tolerance of the fabrication of that specific fab. So what are the waveguide width variation? What are the minimum gap they can open? And what is the error on the gap they get? This kind of information.
Okay.
If you get that, then you can throw this information in the design flow.
Okay. But such kind of analysis can also be carried out using numerical?
Well, numerical is a simulator. So yeah, it just simulates the design you give it. So if you know how the fabrication modifies your geometry, then yeah, sure, you just feed this new modified geometry to numerical, and you get the modified optical response. If you do a statistical analysis, then you do this process many times,
okay,
and you build up your statistics.
Okay, I think that's it from my side. Since I was interested in this ring resonators, I thought I'll just clarify a few things from this.
Sure.
Yeah,
sure.
Thanks once again.
You're welcome.
Thank you.
Any other participants? Fine. As Dr. Daniel has posted his email ID, so anyone wants to contact him further for any queries, you can feel free to contact him.
Absolutely.
Yeah. Nothing I can do.
Yes, thank you very much, sir. I'm sure that everyone's doubts are cleared and all are benefited from the session. I request all the participants to fill the feedback form that's posted in the chat box. And also tomorrow we have Dr. Ahmad Faruqi from University of Bristol, UK, talking on teleportation on a photonic chip. So I request all the participants to join us tomorrow also. And I thank everyone who has joined today. Thank you.
HOD, sir, if you want to say a few words.
Yes, absolutely. Thanks again. It was really a pleasure. I would have loved to be there with you physically. That would be really amazing. And
Sure.
unfortunately, we have to do
being a
what we
travel
can.
lecturer, then maybe shortly we can expect you. Once the pandemic is over, we'll just invite
absolutely you. That would be my real great pleasure.
Yes.
So thanks again for having me, and all the best with this new initiative, this new student initiative, which is really great, and I'm sure will be very successful.
Thank you, sir.
Thank you, sir.
Thanks again.
Thank you, Dr. Daniel. I think, did you get any update from Terence from OSA?
Not as of a couple of hours ago.
Okay, then I'll just update him that we have had this lecture. Maybe we'll follow it back and see to it that how it goes on. So I'll just update him. Yeah, thanks once again.
Thanks.
Yeah.
So HOD sir, you want to say a few words, sir?
Ma'am, I think indeed everything went well.
Yes, sir.
And I'm glad that our guys will got so much of thing on this, especially design and development of gratings and how do we look at into. That's what, as you rightly said, sometimes, most of the times we go trial and error case. So, but there is a process based on that. We have to go statistical process or analytical kind of thing. I think this will open an eye to all our researchers to use analytical equations also to make the design in a better way. Or that's what same we say optimization. So I'm glad that Daniel stressed that point, and I hope all other young researchers, yes, though he has given his email, but ask him in a proper way, in a very what I can say. If you have any problem encounter, you can request him. Not that just support him, send a code and all these things. So have some discuss with him in a professional manner. Thank you, Daniel, once again sharing your knowledge. And I'm glad, as I said, we hope you will visit soon in Chennai. Thank you very much.
Thank you again.
Thank you, sir.
Yeah.
Thank you.
Thank you, sir.
Thank you. So, Dr. Daniel, if time permits, you can join us for tomorrow's session as well, if time permits. It's at 2 p.m.
Okay. Thank you. Thanks for the invitation.
Thank you.